Unit 2, Section 4 is on trigonometric derivatives. So by the end of this video, hopefully you'll be able to find and prove the rules for the derivatives of the 6 primary trigonometric functions: sine, cosine, tangent, cotangent, secant, and cosecant. So just something that comes up a lot. Make sure you know the difference between the reciprocal functions. Like, for example, the reciprocal of sine is cosecant. The inverse function for sine is inverse sine or arcsine. And the cofunction for sine is cosine. For some reason, a lot of students get those mixed up, I think because it's all just non-preciseness. Anyway, so if we are going to figure out the derivative of sine, maybe we can get some good ideas here first about what that's going to look like. And, well, the derivative tells you the slope of a function at a point, the instantaneous rate of change of the function at a point, all that sort of stuff. And the derivative of a function is also a function. So we're going to try to get some intuition by imagining what that derivative graph looks like. And you know, right here, sine, well, actually in a lot of places, sine has horizontal tangents. So at those same x values, the derivative graph for sine would have an output of 0, since derivative tells us slope at a point. So I know at least these 4 points, pi half 0, 3 pi half 0, negative pi half 0, are going to be on this derivative graph. So let's look here in between negative pi halves and pi halves. So in between negative pi halves and pi halves, sine is increasing. Sine has a positive rate of change. All the slopes of any tangent line we could draw are all positive. And so what that means is in between pi halves and negative pi halves, the derivative of sine is going to be above the x-axis. But what you'll notice is right here, just to the right of negative pi halves, and right here, just to the left of positive pi halves, the slope of a tangent line, the derivative of sine, is going to be positive, but kind of a small number. As we look closer and closer to, I guess, halfway in between, what you should notice is the slopes kind of on this side get steeper and steeper and steeper, less steep, less steep, less steep towards pi halves. And so there's kind of a mirroring thing. So I guess that means the slope of sine at a point, the derivative of sine at a point, is going to be the largest here at x equals 0. So sketching here, the derivative graph is going to be like 0, more, up until x equals 0, and then less. Okay? And then in between pi halves and 3 pi halves, we see something similar. So that's a slope of 0, a negative slope, a steeper negative slope. At pi, it looks like the steepest negative slope of the derivative. Oh, I said slope of the derivative. That's not true. Slope of sine, which is the derivative. So we're going to get a similar sort of shape here, where the slope of sine decreases until pi and then increases back until 3 pi halves. So you might be thinking, well, that function looks kind of familiar. I think it's important to do things from maybe not first principles, but building on other things we know. So even if you've realized, hey, the derivative of sine, I think, is cosine, and that's correct, you should be able to prove that. So if we're going to do that, we're going to do the formal derivative of sine. Limit as h goes to 0 of sine of x plus h minus sine of x over x plus h minus x. Now, pretty obviously, that's the wrong color. How about we get something brighter? Pretty obviously, these x's in the denominator are going to subtract, but that wouldn't really leave us with much, because if we put 0 in, that's not the right place to do it. It's h approaches 0. If we put 0 in for h, we're going to get sine of x minus sine of x, which is 0, over 0. And, well, that doesn't really give us anything in terms of evaluating a limit. So what you need to do is expand sine of x plus h. Sine, cosine, cosine, sine. Or at least that's the order I do it. All right, sine of a sum of angles. Excuse me. And so looking through there, if we put a 0 in for h right now, let's see. Cosine of 0 would be 1, so that'd be sine of x plus sine of 0 is 0, so that term would go to 0, and minus sine of x. We still have 0 over 0, so I guess we need to keep rearranging. And what I hope you notice is, hey, sine of x shows up in two places here. Let's move those together. So I'll leave sine of x, cosine of h out front, and then minus sine of x next. And then I guess cosine x sine h just kind of gets moved over here. All right, so I need some more room. And, well, what could we do? Oh, these both have sine of x. Maybe it would help if we factored that out. Well, if I factor out sine of x, I'm going to be left with cosine of h minus 1. And that should look kind of familiar, because the limit as h goes to 0 of cosine h minus 1 is something, well, if you're in my class, you would have memorized, and hopefully you've proven back in limits. So we'll put the h there, and then over here, we're going to put the h under sine of h. So now we have basically four things to take the limit of. And I suppose I could have had an extra limit as h approaches 0 here. Now the nice part about limits is everything kind of works like you expect. The limit of two functions multiplied together is just the two limits multiplied together. So limit as h goes to 0 of sine of x is simply sine of x. The limit as h goes to 0 of cosine of x, well, there's no h there, it's just cosine of x. So let's ignore that cosine of x because we've already taken care of it. The limit as h goes to 0 of sine h over h. Well, sine of 0 is 0 over 0. Oh, right, that's a limit we were supposed to multiply. Limit as h goes to 0 of sine h over h is 1. And let's see, limit as h goes to 0 of cosine h minus 1 over h. Well, what happens there? Well, cosine of 0 is 1. Minus 1 is 0 over another 0. And again, that's a memorized limit, hopefully. And so we end up with, well, sine of x times 0 is 0. And we end up with the derivative of sine of x is cosine of x. So we can think through a very similar process here for trying to figure out what the derivative of cosine looks like. The easiest slopes to pick out are horizontal tangents, where the derivative is equal to 0. So that's going to be, hey, at pi, at 0, negative pi. So the derivative of cosine would be equal to 0, have an output of 0 at those spots and a whole bunch more. Now in between 0 and pi, cosine is decreasing. Cosine has a negative rate of change. Cosine has a negative derivative at all points. All of these tangent lines that I could imagine would have negative slopes, and those slopes would be the most negative at pi halves. So that derivative of cosine would be 0, more negative, more negative, more negative, most negative at pi halves, increasing but still negative up until pi. In between negative pi and 0, cosine increases. Cosine has a positive rate of change. Cosine must have a positive first derivative. All of these little tangent slopes would be positive, and most positive at pi halves. So again, we see something similar, but notice that's actually not what you might expect sine, because sine is definitely not negative between 0 and pi. So how would we find the formal derivative of cosine? Well, really similar process to the formal derivative of sine. Start out with limit as h goes to 0, cosine of x plus h minus cosine x over x plus h minus x. Just like with the formal derivative of sine, we get the x's to subtract, and well, dang, if I substitute in 0, I'll have cosine x minus cosine x over 0. So 0 over 0. I must need to rearrange. And how do we rearrange? We expand cosine of a sum of angles to be cosine cosine minus sine sine. Remember, these do not match. They're opposites when we're doing cosine of a sum or difference of angles. Okay, so cosine x cosine h minus sine x sine h minus cosine x all over h. Limit as h goes to 0. So what can we do here? Similar process. So we see a cosine x in two terms. Let's rearrange to bring those together. So cosine x cosine h minus that cosine x, and we'll just bring negative sine x sine h off to the side. But we actually don't get anything useful yet if we substitute 0 in for all the h's, because that would be, well, cosine of 0 is 1, so cosine x minus cosine x is 0, minus 0 over 0. Okay, so we must need to do something, and that thing is factoring out our cosine of x, and we're left with cosine h minus 1 over h. And out of this last term, we end up with negative sine of x, and we might as well put our h under sine of h. Those feel like they go together. Limit as h goes to 0 of cosine x is cosine x. Limit as h goes to 0 of this whole structure is 0. Limit as h goes to 0 of negative sine of x is negative sine of x. And limit as h goes to 0 of sine h over h is 1. So we get that the derivative of cosine is negative sine. Now, maybe I should mention this. Hopefully, you're keeping a list of all of these derivatives as we create them. I don't think it's a great idea to just look up all these rules on the internet because you don't really have meaning to them. I know you're watching this on the internet, but you should be able to know where these things come from. You have a better chance of retaining them. It should be your knowledge. So the nice part is we don't need to do the formal derivative of tangent. We don't need to do the formal derivative of secant. Secant, tangent, cosecant, cotangent can be written in terms of sine and cosine. And so if you know that and you know the quotient rule, which, gosh, hopefully you do by now, we can find the derivative of tangent a little bit easier. All right, so if we're not doing formal derivative, well, I can't really do the derivative of tangent, so I might as well rearrange into something I can deal with, and that is, well, tangent can be written as sine over cosine. And if we're doing sine over cosine, well, that's a quotient of two functions, and the derivative of a quotient of two functions is the denominator, cosine, times the derivative of the numerator, minus the numerator, sine, times the derivative of the denominator. And, well, I kind of changed signs here, so maybe I'll make that a little more obvious. Struggling with my video. So this used to be minus sine of x, negative sine of x, and I just changed those both to be positive. Okay, so the derivative of a quotient of two functions is the denominator times the derivative of the numerator minus the numerator times derivative of the denominator all over the denominator squared. And then, well, that looks pretty complicated, but it's not that bad because in the numerator, cosine times cosine is cosine squared, sine times sine is sine squared, and so that's a Pythagorean identity. Sine squared plus cosine squared is 1. And then, well, we actually like cosine better than we do secant, but we like to have everything in the numerator, so we think of tangent. Tangent has the derivative of secant squared. If you understood that, you actually don't need me for the other three trigonometric derivatives. you can figure out what we're going to do to find the derivative of cotangent of x. How would you do that? Well, you would think of cotangent as cosine over sine. And how would you do the derivative of that? Well, cosine over sine is a quotient of two functions. So the derivative of a quotient of two functions is the denominator, sine, times the derivative of the numerator, and the derivative of cosine is negative sine, minus the numerator, cosine, times the derivative of the denominator, derivative of sine is cosine, all over the denominator squared. And then again, we rearrange, and sine times negative sine is negative sine squared. Cosine times cosine is cosine squared. If you factor out the negative in the numerator, we again see, hey, that's going to be sine squared plus cosine squared is 1. And 1 over sine squared is cosecant squared. So the derivative of cotangent is negative cosecant squared. To find the derivative of secant, very similar process, except we actually get a little bit easier. Secant is the reciprocal of cosine, so we can just write that as 1 over cosine, because now we know the quotient rule. We know the derivative of cosine, pretty straightforward. The derivative of a quotient of two functions is the denominator, cosine, times the derivative of the numerator, derivative of 1 is 0, minus the numerator, and again, this used to be minus. The numerator is 1 times the derivative of the denominator. Derivative of cosine is negative sine. So instead of writing a minus and negative, I just change the subtraction in between the two terms in the numerator to be an addition. Anyways, all over the denominator squared. And cosine times 0 is, of course, 0. And so it's kind of all about rearranging for things to match. I like in this order because I really like the book Calculus for Dummies. And this is the order that went in. So anyways, we can rearrange 1 over cosine and sine over cosine to get the derivative of secant is secant tangent. All right, one more. How do we find the derivative of cosecant? We, of course, write cosecant as 1 over sine, do the quotient rule. The derivative of a quotient of two functions is the denominator sine times the derivative of the numerator, derivative of 1 is 0, minus the numerator 1 times the derivative of the denominator, derivative of sine is cosine, all over the denominator squared. And let's see. Sine times 0 is 0. 1 over sine is cosecant. Cosine over sine is cotangent. So we end up with the derivative of cosecant is negative cosecant cotangent. So a couple of examples to see how we'd put this together, because now we can do a little bit more complicated derivatives. So how would we find the derivative of x squared times sine of x? Well, you can see x squared is a function, sine is another function, so we need to use the product rule. And the derivative of a product of two functions is the first function, x squared, times the derivative of the second function, derivative of sine is cosine, plus the second function sine times the derivative of the first, and the derivative of x squared is 2x. So this is a great result, pretty easy, but if we're going to be doing more, finding maximums and minimums, we always want to rearrange so that it's easy to set our derivative equal to 0. We're just kind of thinking ahead here. So I'm going to factor out the x, the common factor, just so that'll be easier in the future. If that doesn't make sense, don't worry about it. Now, how could we find the derivative of sine of x all squared? Well, at this point in my class, we don't know the chain rule. So the only thing we know is product rule, quotient rule, power rule, and these trigonometric derivatives. So we have to rearrange, avoiding something we don't know. There is a way to do it. We're just not there yet. We don't know how to, we know how to do x squared, the derivative of x squared. We don't know the derivative of sine squared directly yet. So we can just think of that as a product of two functions. The derivative of a product of two functions is the first function sine times the derivative of the second function. The derivative of sine is cosine plus this. Did that backwards. Second function sine times the derivative of the first, cosine. So anyways, we probably want to simplify, and that's 2 sine cosine, except for that's not the way we're going to leave it. We're going to rewrite that as sine of 2x. Number 1 to remind you, and number 2 because that's probably the way it'd be written as multiple choice. Sine of 2x, don't forget, is sine of x plus x, which is the same thing as sine of the first x, cosine of the second x, plus cosine of the first x, sine of the second x, which is what we had back here. So you really need to know those trigonometric identities. All right, so how would we find the derivative of cosine squared? Well, again, we can't use the power rule directly yet, so we just think of that as cosine times cosine, which is going to have a derivative of first function times the derivative of the second, plus the second function times the derivative of the first. And you can see cosine times negative sine, another cosine times negative sine is, well, 2 of those negative sine cosines. And again, we use that same identity, that 2 sine cosine is the same as sine of 2x. All right, so we're given sine of x all squared plus cosine times cosine. How would we find that derivative? And well, right now you might be thinking, hey, we just did that. And you're right. So the derivative of sine of x all squared is sine of 2x. The derivative of cosine times cosine is negative sine of 2x. But what you should kind of always be thinking is, hey, maybe I can rearrange before I do the derivative. And hopefully you realize sine squared plus cosine squared, Pythagorean identity is 1. And so if you knew that, the derivative part is incredibly easy, because you would just be taking the derivative of 1, which happens to be 0. Couple more examples. The derivative of 2x cubed secant x. How would you deal with that? Well, that's just another product rule. Pretty straightforward. The derivative of a product of 2 functions is the first function times the derivative of the second. We found that the derivative of secant was secant tangent earlier, plus the second function, secant, times the derivative of the first. The derivative of 2x cubed is 6x squared. And why would I rearrange? Well, you don't have to, but in the future, we're going to be using derivatives to find maximums and minimums, which almost always occur, especially for functions like these, at horizontal tangents. So we'd be setting that derivative equal to 0. So it'd be much easier to say 2x squared equals 0, secant x equals 0, x tangent x plus 3 equals 0. Well, that's where we're going, and that's why I would write it that way right now. Pretty straightforward to find the derivative of h of x, or 2x plus 1 all times tangent x. Another product of 2 functions, and the derivative of a product of 2 functions is the first function, times the derivative of the second function, derivative of tangent is secant squared, plus the second function, times the derivative of the first, and the derivative of 2x plus 1 is 2. Not much to rearrange here. I just multiplied it out. 2x times secant squared plus 1 times secant squared plus 2 tangent x. I like having that 2 out front. That's a lot more obvious that the 2 has nothing to do with x inside the tangent. All right, last one. How the heck would you find the derivative of this? X squared tangent times secant. And the problem is this is 3 factors multiplied together, and the product rule we've memorized only has 2. So the best way to do that is to think of this as 2 functions. So the derivative of a product of 2 functions is the first function. So I just write that x squared tangent of x down, times the derivative of the second function. And maybe you just leave that blank for a second, and you'll come back and rewrite it, because that's a little bit harder than writing down the second function, easy to copy, times the derivative of the first function. And then when I go back and rewrite everything, it looks like I'm smarter than I am, and I can just do everything all at once. So the derivative of a product of two functions is the first function. I wrote that times the derivative of the second. Derivative of secant is secant tangent. Plus the second function secant times the derivative of the first. And the reason this is complicated is we have another product of two functions that we're thinking of as our first function. So the derivative of that product of two functions, let's change the color, is the first function, x squared, times the derivative of the second, derivative of tangent is secant squared, plus the second function, tangent, times the derivative of the first, and derivative of x squared is 2x. I'm going to put parentheses around this tangent. That'll be pretty obvious that the 2x is separate. And hopefully you realize there's not going to be a ton of simplification, so we'll just stop there.